As far as we know, there are four fundamental forces in nature. The first two have to do with what happens at the subatomic level. As we may know from junior grades, protons don't like each other. Like charges will repel, like these two right now. All right, but how does that explain how the nucleus is able to hold itself together with so many protons there? Well, that has to do with the strong force. As long as you bring these two protons close enough to each other, they will stick just like that. Of course, if you have enough of these, over time they may deteriorate and fall apart from each other. And the weak force explains that part of the instability of the nucleus. Another fundamental force is the electromagnetic force. Part electricity, part magnetism. Even though this force may be self-explanatory, there are other forces that it can also explain as well, such as the reason why springs are elastic or even why friction exists. And the force that we're going to be talking about today is the gravitational force. Sir Isaac Newton once said this, that there's an inherent attraction between all objects. This force is proportionate to the product of the masses and inversely correlated to the distance of separation squared. Why did he use a proportionate symbol? Well, it's because he knew that there was a constant, but that constant would have been a very small number, 0.000000000 something something something. All right, he didn't know what it was, but he knew that objects did like each other. Now, the larger the object was, the easier it was to measure it, but it was still a very small value. And unfortunately, just like all the people, he died and he wasn't able to figure out that mystery number. Luckily, today, we do know what that mystery number is. That value of g is 6.67 times 10 to the negative 11 newtons times meters squared all over kilograms squared, also known as the universal gravitational constant. As for the rest of the measurements, make sure you stick with what is memorized in physics class as the MKS system. So make sure that your distances are measured in meters, your mass is measured in kilograms. With that said and done, how about we go through this first example together? Think of you and someone who you are attracted to. You can fill that in the blanks below. What is the force of attraction between you two? Have you tried it out yet? Well, let's take it up together. All right, first off, it's a word problem. Start off with your givens. What do you know? You state the formula. You sub all the values in, including units. And then after careful calculations of this in your calculator, how about I go through a sample with you? All right, 6.67, and you want to use this button over here, times 10 to, because it's going to glue everything together. There's two minus signs. We want to use negative, not subtract. And that's how you would type in a power value. We're going to multiply this by 150, multiplied by 50, and divide by the distance of separation squared. Now, even though it says 200 centimeters in the story, we need to stick with meters. So divide by 2 squared. And you're going to get a very small answer. All right, something times 10 to the negative 7. It's really tiny. Now, you know that a newton is the equivalent weight of an apple. Imagine taking that apple and just scraping off the wax of it, just barely scraping it. That little amount of mass is equivalent to the attraction between you and somebody else if you guys were separated by a desk in the classroom. All right, we know that this force is naturally an attractive force, and that's why some textbooks would have a minus sign in the formula. To me, it doesn't matter if you have a minus sign there or not. We just know naturally that gravity is just an attractional force. All right. We have yet to discover this thing called anti-gravity, but the math says, you know what, it is quite possible if you could find an anti-mass. All right, so how exactly was this value of g discovered? It was determined about 100 years after Newton's death by a young man named Henry Cavendish. Now, he's not the original person to think about this crazy mechanism. He actually copied off somebody else who was doing a similar experiment at that time as well. And that was Charles Ampere, where he was trying to figure out the force of attraction between two objects electrostatically. If you've ever taken a balloon before and rubbed it against your head, you notice that balloon will stick to the wall. So what value, what numerical value of attraction was that? And the way how he figured it out was that he had these two separate charges. And to be able to make sure that it floats in space, he would put it on a balance. And that balance would be attached to a string that you could generate a little bit of torque in your forces of attraction or repulsion. All right. So when he placed the other mass nearby that it was attracted to, it would start twisting, and you could measure that twisting force. So he would double the charge, figure out the twisting force, maybe half the charge, and measure the twisting force. Put it twice as far, measure the twisting force. Put it at half the distance, and still measure the twisting force. And he determined the correlation between charges and their force of attraction. And guess what? It looked like that. Not much different than our formula that we're covering here. So Henry Cavendish looked at that experiment and says, hey, how about I do the same thing too? So he cleared out his entire barn, and he had these two huge boulders, probably as tall as you and me. All right. And he had them suspended. That way they're able to float in his barn. Then he had these two smaller masses that he would bring close to it and cause the whole system to twist. And as it twisted, it caused this mass to rise and fall. So he did the experiment over and over and over again, plotted out his correlation, and he found out that in his correlation, the slope worked out to this number over here. Compare that with today's value. And that's pretty amazing. Kind of reminds me of another dude. You may be familiar with this guy here. Exactly. He built this in a barn with a box full of scraps. And if you look at the numerical error, it was about 1.2% different than what is today. That's kind of like me asking you to tell me what a meter is by just marking 2 marks on a wall. And your answer is close to within a centimeter. That's pretty amazing. All right, there's another value of g as well, and it's little g, and that's the gravitational field strength. For example, here on Earth, the gravitational field strength is at 9.81 meters per second squared. But that value does change. The further we are away from the surface of the Earth, the weaker the force of gravitational attraction. And it doesn't just decrease linearly. It decreases as an inverse square correlation. So let's say that you're at the radius of the Earth, all right? So 6,400 kilometers from the surface of the Earth. And you have a weight of approximately 100 kilograms, which is around 1,000 newtons. If you so happen to be double the distance of the radius of the Earth, your weight will decrease. That force of attraction will decrease. Not by half, but by a half times a half, or down to a quarter, roughly 250 newtons. And if you are 2 times away from the surface of the Earth, or 3 times away from the center of the Earth, then your value will decrease by not by a third, but by a third times a third, or down to a ninth. All right, so this value continuously changes, not only by how far you are away from the surface of the Earth or the center of the Earth, but also by the fact that as the Earth rotates, you start generating this fictitious force called a centrifugal force, and that will artificially decrease your force of attraction to the Earth. All right, and that's why the value of g does fluctuate depending upon where you're living. For our purposes of where we live, we'll just accept the value of 9.81. All right. Or just more generally, 9.81 plus minus 0.01 newtons per kilogram, which is also equal to meters per second squared. So how do we figure out the value of g? I mean, yes, we know that here in North America, we're roughly at 9.81 meters per second squared. But how would you find out the value of g on the moon, or even on Mars, or on any other planet? Well, as long as you know the approximate mass of the planet and the radius or diameter of the planet divided by 2, then you could figure out the gravitational field strength. And the way how you do it is with the two equations we just learned. Earlier in this unit, we learned about the formula Fg is equal to mg, and today we learned the formula Fg is equal to gmm over r squared. To make life easier, we're not going to bother writing down m1, m2, and if in your homework you want to drop that notation, by all means, there's another way of stating it. Big M is for the big object, and little m is for the little things like you and me compared to the planet itself. All right, it just cleans up the formula quite a bit. And these two formulae are correct. There's nothing wrong with them. So if they are correct and they are both valid in describing a person's weight or the force of attraction between two objects, then why not just equate them together? And you'll notice that the little m here will divide out with the little m on the other side, and we're left with the value of g. So this is a universal formula used to determine the gravitational field strength on any celestial body: the moon, the earth, Mars, the sun, any given star. On any given unit test, you're expected to derive this formula on your own. It's not too bad. Just equate these two equations together. How about we go through a practice problem now? Okay, what is the gravitational field strength of the Earth when we're as far away as the moon? So if the Earth is all the way over here, there's my North America and Australia. Sure, why not? And let's say you're all the way out here. It's not to scale, all right? As far away as the moon. What is the force of attraction at that distance? Well, you know that if you're at the surface of the Earth, your value of g is equal to 9.81 newtons per kilogram, or 9.81 meters per second squared. But let's say that you're just as far away as where the moon is, but suddenly the moon disappeared. You're still at the same spot. What is your force of attraction? What is the value of g there? Go ahead, calculate it out. All right. The distance that the moon is away from the Earth is this value over here. So you sub it in. And hopefully you got this number over here. This works out to roughly, 3 millimeters per second squared. Compare that with 9.81 meters per second squared. What this tells us is that the moon is constantly falling towards the Earth. All right. But you don't need to worry. Even though the moon is constantly falling towards the Earth, it is also orbiting. And what's happening is that as it's orbiting, it's attracted to the Earth, but then it falls. Then it attracts the Earth, then it's moving, attracts the Earth, then moves, attracts the Earth, and then moves. So it's constantly falling to the Earth, but because it's in motion, it still moves further away from the Earth. And these two values cancel each other out. And that's what results in the moon orbiting around the Earth. So we're glad that the moon is not stationary. All right. But what is that force of attraction now? Okay. Remember, the moon is really, really heavy compared to you and me. So even though it's accelerating at a very slow rate, it's super heavy. So what is that force of attraction? Now, you could use the formula Fg is equal to gm, m over r squared, to solve for that. But since you have the value of g, you could also use Fg is equal to the mass of the moon times this new gravitational field strength at that new distance. Calculate it out. And I hope that either way you do it, you arrive to the same exact answer. That's a lot of apples. 2 times 10 to the 20 newtons. Okay? 2 followed by 20 zeros of apples of attraction. Something that you and I might not notice because we're rather small, but the Earth actually feels it. So as the moon orbits around the Earth actually is attracted to the moon as well. Remember Newton's third law. For every action, there's an equal and opposite reaction. All right. In fact, this is how astronomers actually try to figure out whether if there's a small satellite orbiting around any given planet or any given star system. All right. So if they see a star and they see the star is wobbling in space, it's safe to assume that it's wobbling because there is a body of planets surrounding that star, causing it to move. So yes, even the Earth is manipulating the motion of the sun as well. Not by much, but it is. Okay, but back to this number over here. It's an incredibly huge number, and it does impact the Earth. Now, most things on the Earth are immobile, but the air and something that has more mass than the air, like the ocean water, can move because of the force of the moon. And that's what results in tides here on Earth, or gravitational tides, where when the moon is directly above that body of water, the water is attracted towards it. And as the moon moves away, then it returns back to its rest position. And in some places, it just pendulates and happens multiple times, whether the moon's there or if it's away. It's just that coincidentally, the moon is back there again by the time it comes back. If you've ever been to the Bay of Fundy, that's the exact reason why it experiences 2 tides a day. Once when the moon is nearby, and once again one is further away. For more fun adventures like this, get started on your homework. And if you're still sticking around, that's because you have some questions from the homework. So let's go and do that. Find the force of attraction between a 60 kilogram student and these objects here. So we start off with our formula. Fg is equal to capital G mm over r squared. 6.67 times 10 to the negative 11 newtons times meter squared over kilograms squared. Yes, I expect you to write that down. Times a 60 kilogram student. And this time round, you're comparing it with another object that's 80 kilograms located 1.4 meters away. And hopefully you got this value here, 3678, 8.16. Oops, not 40, 80. There we go. Okay, 367. 1.6 times 10 to the negative 7 newtons. What about a 130-ton blue whale that's 10 meters away? Well, we're talking about a metric ton, so that's equal to 130,000 kilograms. All right, so 1 metric ton is equal to 1,000 kilograms. And this time in your denominator, you have 10. And hopefully you got this answer here. 5.3 times 10 to the negative 6 newtons. A 45-gram golf ball. Don't forget that you need to convert that into kilograms. So 0.045 kilograms. And this time around, they're located 95 centimeters away or 0.95 meters away. Pull out your handy dandy calculator. Backspace to edit. 0.045 divided by 0.95 squared will get you 1.99 times 10 to the negative 10. With all your givens being worst case scenario 2 sig fig, that will round to 2.0 times 10 to the negative 10. Number 2, what is the distance between the moon and the earth, if you're trying to figure that out, if you're given those values there? Now you might be wondering, well, how do I know about the properties of the earth? Well, when you move on to question number 5, that kind of gives away the answer there. All right, so when you look on the lookup table on number 5, it tells you the mass of the earth. So now we have the formula Fg is equal to Gmm over r squared, and we're isolating for r. So r is equal to Gmm over Fg. So 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared times the mass of the earth, where we had to look it up on a lookup table, and the mass of the moon, whoa, copied on the wrong number there. Should be huge. 5.98 times 10 to the 24 kilograms times the moon, which you'll see that the moon is only about 1/100th of the mass of the earth. And their force of attraction is still insane because we've proven that before. 2.00 times 10 to the 20 newtons. Pull out your handy dandy calculator. You'll need to open bracket your square root. 6.67 to the power of negative 11 times 5.98 to the power of 24 times 7.34 to the power of 22 divided by 2 to the power of 20. Close bracket, and then that will give us the distance separation. 3.678, 3.82 times 10 to the 8 meters. All right. Number 3, 2 tankers of equal mass attract each other with a force of that. If they're centimeters of that distance apart, what is the mass of each tanker? Well, for number 3, we can simplify the formula down to this. Fg is equal to G m squared over r squared. After all, the two have the same mass. They are equal masses. Okay. So m times m, or m squared. That way we can isolate for our m. M is equal to fg times r squared over g square rooted. And optionally, if you want to, it's still the same answer, r root fg over g. So they're separated by 85 meters, and we find out that their force of attraction is still quite significant, 3500 apples. All right, so two large objects will attract to each other inherently. Divide that by 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. Yes, always include units in your solution. 85 times the square root of 3,500 divided by 6.67 to the power of negative 11, and then we get 3,678. 6.2 times 10 to the 8 kilograms. Number 4, find a person's weight. All right, I'll just use the Earth's example. Once again, we're supposed to use the values from question number 5. So, if you're trying to figure out the person's weight, that's their force of attraction, which is equal to gmm over r squared. So for the first example, it's g times, or let me write it out, 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared times the mass of the Earth, 5.98 times 10 to the 24 kilograms, and the mass of you, 68 kilograms. And the first question is from the surface of the Earth. So you know that the radius of the Earth is 6.38 times 10 to the 6 meters squared. Okay, so that's our first case. To the power of 6. And if you're not comfortable and you want to put brackets before you square it, by all means, because when you place a squared, how does it impact this question? Does it square the 6 or does it square everything? You need to know your calculator. I know this calculator, when I place that square, it automatically assumes that 6.38 times 10 to the 6 is already in brackets, because that's what times 10 to the power does. So if I want to square the 6, then I need to place brackets around the 6 squared, but otherwise this will give the correct answer. All right. 667 newtons, at least with the values, or 666 with whatever values that are given to me here. Okay. Well, what about at the top of Mount Everest? Well, with Mount Everest, then what I need to do is that in the denominator, I need to add the height of Mount Everest along with the radius of the Earth. All right, so 8848 needs to be added on top of that. So here I will just add 8848 meters into my problem. All right, so in this version here, the value should drop down, 664 newtons. And what about at 2.5 times the radius of the Earth? Well, then I would just take this value over here and would just multiply it by 2.5. And that'll give me that value of 107 newtons. Done. As for number 5, calculate the gravitational field strength on the surface of the following planets. We're just looking for a g. The little g is equal to capital G, mass of the planet, divided by the radius of the planet squared. And these values aren't impossible to solve for. If you're curious on how they can figure that out, first off, you can remotely figure out the approximate density of the mass of the planet, mostly based upon spectronomy. It's by looking at the wavelengths of light that are emitted off the surface of the planet. Then you can figure out the typical composition of it. In fact, that's how we figure out the chemical composition of the gases emitted by the different stars. All right, just by looking at what wavelengths of light are emitted. So the mass can be determined by figuring out, first off, the density of the primary ingredient of the planet. All right, density is, after all, equal to mass over volume. And for volume of any given sphere, well, volume is equal to 4 over 3 pi r cubed. And even though we're here on Earth observing a star from very far away, if you have a calibrated telescope, you should be able to figure out the diameter of the planet. That should be discernible. And as the Earth orbits around the Sun, every night it's going to be in a different location. And as it's in a different location, you can observe the same planet or star again, and by that you can triangulate and figure out how far away it is from you. So the value of r of the distance of separation can be solved for, and the mass can be solved by figuring out the approximate density of it, determining the volume, and finding the radius of it by triangulation. So it's all measurable. And number 6, what would an object weighing 1,000 newtons on Earth weigh on Mars? Remember that this is a weight, so you got to first figure out the corresponding mass. Fg is equal to mg. So the mass of the object is equal to the force of attraction the object has on the Earth. So 1,000 newtons divided by 9.81 newtons per kilogram equals 101.94 kilograms. Yep, just carrying 2 extra sig fig. Now we can figure it out on Mars. So we need to know the property on Mars, where if you did question number 5, you'd find out that the acceleration on Mars is equal to 3.61 newtons per kilogram. So the force of gravity on that planet is equal to m times g of that planet. So 101.94 kilograms times 3.61 newtons per kilogram will give you roughly 360 newtons. There you go, 368 newtons. And that's how you answer the homework questions. Catch you later.